Welcome. The title of today's notes worksheet is Exponential Functions. And so this lesson offers us an opportunity to explore exponential functions in further detail. We'll do a couple examples to review from yesterday's lesson, and then also probably focus more on the graphical aspects of exponential functions, talk about some of those characteristics a little bit. So let's get started here. Example 1 at the top, it says a fully inflated beach ball loses 6% of its air every day. If the beach ball originally contains 4,000 cubic centimeters of air, how many cubic centimeters does it contain in 10 days? So just remember what we kind of talked about yesterday is a quantity that increases or decreases by a constant percentage can be modeled with an exponential function. And so let's get the ball rolling here and just go ahead and put y equals a times b to the x. And let's see what we have going. So it looks like, I guess what I'm going to do first is try to write a model to sort of relate the two variable quantities. In this case, it seems like it's the volume of the beach ball and time in terms of days. So I'm going to go ahead with v as my dependent variable there. And remember that little a value represents the initial quantity, so I'm seeing this as 4,000 cubic centimeters. So let's start out with that. Now to me, everything revolves around that b value. And so what I'd ask you to do is pause the video for just a moment and see if you can write in the appropriate b value for this scenario right up here. Okay, well, let's see how you did. When I did this one, I looked at losing 6% was 1 minus 0.06. So that's where that value comes into play. And so then we would basically be multiplying by 0.94 repeatedly. And as we talked about, repeated multiplication is raising it to an exponent. So if you're not sure where that 0.94 came from, I'll just write it above here, I suppose. What I did is exponential decay, 1 minus the percent decrease. So 1 minus 0.06. Nice. Now for any t, we should be able to find v. For any v, we would use the graphing calculator at this point in time, but we would be able to find t. So what I see is 10 days, and so let's go ahead and keep this nice and easy here. So I get 4,000 times 0.94 and raised to the 10th. If you have an opportunity to grab the calculator and go ahead and pull that off, I have mine on my paper already, so I'll go ahead and write my answer, and I'll hope you'll agree with it, but basically it would be about this, give or take, and that was in cubic centimeters. So just a very quick review problem to connect from yesterday's lesson. And then, as I said, we'll focus on some more of the graphical characteristics coming up here on the rest of the notes worksheet. So let's go to example 2. It looks like it's broken up into 4 parts here. What I would love to do is just kind of for the first time see what a nice looking exponential growth curve will look like, and maybe do a few transformations off of that. That's what would be the B, C, and D components to this particular example. Now, I rarely ever have students do this, but I think it benefits us here to actually see some of the points on the graph of the function and then be able to sort of point plot and then see if we can get some type of good graphical pattern on the coordinate plane. So in this case, what it should form is a nice looking exponential growth curve. So anyway, here's what I'm thinking. Let's go ahead and just do a few x's. I'm just going to keep it nice and simple. If you don't mind mirroring me on your paper there, that would be great. And then what we would do is just treat those as our inputs and then come up with the appropriate outputs and then just kind of plot them and see what type of pattern emerges. So I'm going to start out with actually I'm going to go backwards if that's okay with you. Not that it matters a ton here, but these would be my x values. So I'm going to put in 3 for x, and so just 2 to the 3rd. And 2 to the 3rd would, of course, give us 8. Then just go ahead and write back in, use that as your input, so 2 squared, that would be 4. There's your input, so 2 to the 1st, 2. 2 to the 0, everybody. Remember that from way back when. 2 to the 0 is definitely 1. And now, remember how negative exponents work. So, and keep this in mind because this is going to come up a lot during this unit conceptually. The exponent can be negative. I can do 2 to the negative 1st, 2 to the negative 2nd, 2 to the negative 3rd. But think about this from a number sense standpoint. What type of answers do I get when I apply these negative exponents? Well, 2 to the negative 1st, as you remember, is 1 over 2 to the 1st, or 1/2. 2 to the negative 2nd is 1 over 2 to the 2nd, or really 1 over 4. And 2 to the negative 3rd is really 1 over 2 to the 3rd, or really, in this case, 1/8. And the further we go into the negatives, the closer, as you can see, these get to 0. But I guess I would ask you this again because it's going to come up in the future. Will these numbers always be positive? Absolutely. Okay, so please keep that in mind. Well, anyway, let's plot some points here. Let's get going with this. So I see 0, 1, 1, 2, 2, 4, 3, 8. Looks like it's up here, and then -1, 1/2. So as I said, just as best as you can, especially on these. But basically, you would see the further we go into the negatives, the closer those values would be getting to 0. And you can start to see a nice looking exponential growth curve form, something like that. And so that would be y equals 2 raised to the x. Wonderful. And we'll see some exponential decay curves in action when we pick up the calculator in about 3 or 4 minutes. But in the meantime, let's go ahead and just do some transformations on this piece. So everybody, here's what I started with, y equals 2 to the x. Why don't we treat that as our parent function, and then think about all the transformations we did. And do you happen to remember what happens when I take that original function and I subtract 3? Well, if you remember correctly, this would be a vertical shift just down, so down 3 units. And so let's go ahead and just take our points there. Don't need to worry too much about this, but take each one of those points, if you would, from the original, and if you don't mind, move it down 3 for me. So it would have something like this, and again, just kind of working through nicely here. And here's the situation at hand. We could see we would still do 2 raised to a power and get a positive, but then we would subtract 3, so it goes down 3, probably looking something like this, give or take. And you are more than welcome to grab a calculator and kind of confirm what we draw up here. But I'm seeing that pretty nicely as a 2 to the x minus 3. Okay, good. So just transformations here, working with these. It's a good opportunity to kind of review some stuff from first semester. Okay, let's do this one. I guess I would ask you, if 2 to the x is the parent function, do you happen to recall what this is right here in terms of which transformation out of the 10? And this definitely looks like an input change as opposed to an output change. So it's going to be horizontal in nature. And if you remember, it is a horizontal shift. I guess I would ask you this. Does our graph move to the left 3 or to the right 3? And if you remember correctly, it moves to the right. So again, let's just take a moment there if we can. And what do you say we just take each of the original points, and how about move it to the right 3? So I'm going to do that up here. If I'm ahead of you a touch, feel free to pause that video at any time. But basically just move it, everything to the right 3. And you get something like this, give or take. Not getting too close there. So something like that. Probably could have done a little nicer job on this end, getting closer and closer and closer to 0 there. Never going to quite touch. And we'll talk about that piece sort of going forward. But yeah, it looks like I do have a horizontal boundary line right there. I had one up on the original, same spot. And this one, I had a horizontal boundary line that moved down 3 units. Okay. What do you say we take this one maybe in 2 steps? So let's sort of redraw, and because I have 2 transformations here, let's go ahead and name those transformations and then kind of go forward from there. So from 2 to the x to 2 to the negative x. Hopefully you may recall that that is one of the transformations. It's a reflection piece, and as a matter of fact, it's a y-axis reflection. So by changing all the inputs to their opposites, we reflect the original graph over the y-axis. So what do you say we do that? And I'm going to do it dotted on mine. You can maybe just do it light, however you want. It's totally your call on this. But what I'm going to do is take all of the points on the original graph, and I'm going to reflect them over the y-axis. And so as a matter of fact, that would come here. This one moves over here. This one moved here and here. So again, just sort of flipping everything over the y-axis. Not a big deal here. Kind of getting closer and closer to 0 on that end. And so when you get an opportunity, see if you can draw a nice looking exponential decay curve, as a matter of fact. That's what that would be right there. Oh, and I meant to do it dotted. Oh well, that's all right. So what I'll do is put a little 1 by this, and how about a little 1 by that, and just sort of the first step, so to speak. Okay, and then I guess what would be the secondary transformation there, just kind of bringing that forward. It looks like after I do my 2 to the negative x, what am I going to do to this entire graph when I add 2? And as you can see from problem B, it looks like it is the same format, except this one's going up. So it looks like this is a vertical shift. And so everybody, when you get a chance there, what do you say you take each of those points and move them up 2? And let's see if that works for us. Something like that. And something like this. There we go. And so now, especially that horizontal boundary line, keep that in mind if you would, but that horizontal boundary line also moved up to 2. And so I'll do that right there. And that was our final one. I'm going to actually just bring our graphing calculator up. You could just hold off for a sec. I might as well go ahead and take a look at it briefly here. So let's see. I'm going to go to my y equals and do 2 raised to the negative x. And how about a plus 2? And let's go ahead and just zoom standard and see how well we did there. And so you can see what I drew. Turned from exponential growth to exponential decay. And you could see everything moved up 2 as I get a horizontal boundary line at 2 as opposed to 0. Okay, not bad. So just want you to get comfortable with some of those. We'll go ahead and take a look and see if we can put some pieces together here with the graphs, and now understanding that exponential models, of course, are all based on a percent increase over the time period for exponential growth, or a percent increase in a time period based on exponential decay. So let's go for it. There's an investigation on your sheet, and it says exponential growth and decay curves, just using this model right here. I'm going to keep the a value at 1 in each case, just to kind of keep it nice and simple. And here's what I guess I'd ask us to do. If you don't mind, can you take a moment and let's fill in, let's do these columns first. Let's take care of that. So if everyone doesn't mind, pause the video for a second and give me percent increase for those exponential growth models. And then this one's a little harder, everybody. See if you can do a percent decrease for the exponential decay models. So pause and then come on back. Okay, well, let's take a peek here. When I looked at these, I got this one as a 2.1%. And just remember, and I'll do this for each one just in case, that's what that B value is made up of. So there's your 2.1%. This would be 10%. Same scenario. This is 1 plus 0.1. Hopefully that helps, and feel free to write that in there if it does. This was a 50% increase. So this would be 1 plus 0.5, 0.5 being your 50%. This is a great one. We're going to do some doubling problems in the near future. So when something doubles, that would be repeatedly multiplying it by 2. But that definitely does translate into a percentage increase. And as a matter of fact, something that doubles increases by 100%. Because that B value, of course, is 1 plus 1. And the number 1, as a percentage, is 100%. A quantity that triples in a particular time period, or repeatedly triples here in this case. So it's exponential growth, growth factor of 3. That would be a 200% increase in its quantity. So something that triples increases by 200%, because of course that B value would be 1 plus 2. And there's your 200% right here. Wonderful. Now just be careful on these. When I look at this, 0.95 is our decay rate. That doesn't mean the percent decrease is 0.95. It means that it's 0.05, which would be 5%. So just kind of looking at this piece, remember exponential decay, everybody, is 1 minus the percent decrease. So 1 minus 0.05 to get us there. This one, everybody, I got about 17.6%. Same scenario in order to get that number right there. That's how we do it. And this one, this is a halving. So in this case, it looks like a 50% decrease. And 1 minus 0.5 would get us there. 0.1, everybody. So that would be a 90% decrease. because it's 1 minus 0.9 in order to get us that 0.1 as our decay factor. And last but not least, this one down here seems like it would be a 98% decrease every time period if this is my decay rate right here. So this would be 1 minus 0.98. Now, I guess I would ask us in terms of exponential growth and decay curves before we go ahead and put these on the calculator. Which do you think in terms of exponential growth would be the steeper curves? So steeper exponential growth, do you think these towards the top or these towards the bottom would be steeper? Well, let's go ahead and see. So let's do the growth and decay sort of separate here. And I'm going to do it all at once. I know we're not going to be able to create the best window in one shot for all 5 of these, but I'm still going to do it. And if it's okay with you, instead of writing 1 times for each of these, I can avoid that and just do that b value. So this would be 1.021 raised to the x, and then 1.1 raised to the x. I'll keep going, and if you could actually do it as well, that would be great. 1.5 raised to the x. We've already seen 2 raised to the x. And how about 3 raised to the x? All right, so remember what I asked there. Which do you think will be the steeper curves, these towards the top or these towards the bottom? And I need you to start thinking about a couple characteristics here. Specifically, and this will show up on the back side of your notes worksheet, talk to me about domain and range, and you'll see a couple other ideas as well. So really focus in on the nature of the curves there, and then we'll see if we can answer those characteristics. All right, everyone, I'm going to go ahead and hit graph at this stage. That one's pretty flat, and so it does look like the bigger the number, obviously the greater the exponential growth, so the steeper the curve. So this was the 1.5 to the x, the 2 to the x, this is the 3 to the x, and so forth. The others, especially on this window, pretty flat. Okay, well, I'm going to go back to the y equals here, everyone, and clear those out. I would ask you the same thing on these decay functions. So which do you think would be the steeper curves, exponential decay? Do you think these would be steeper, or do you think these would be steeper? Yeah, think about it for a second, and think about the nature of where this rate came from, how it came into being, and then let's see. So I'm going to do the same thing. I'd ask you to go ahead and graph as well. There's my 0.95, 0.824, and just plugging through nicely here. Let me make sure I get all of these typed in correctly. And as I said, keep in mind domain and range specifically. And if you flip your page over and see a couple other ideas as well, I'd like to get your feedback on that. So let's see. I'm going to graph. Which are the steeper ones? The ones towards the top, the one towards the bottom. And looks like the ones towards the bottom showed up there as very steep. And why is that, by the way? I have a decay factor of 0.02, yet that showed up as the steepest of the 5. And I'm hoping you would see that the reason it is because it's losing 98% of its value every time period. Every time we move 1 to the right, we lose 98%, far greater than the other percent decreases. So the smaller this number, the greater the percent decrease, I guess is the best way to describe it. All right. Well, it's time to answer those questions, of course. So flip your page over if you would, and especially these two, if you would, tie those together for me and put an asterisk here, as that's going to come up as we look at a couple other things in this unit. But talk to me about just any basic exponential growth and decay model. So you don't have to write this on your paper, but this is what we're focused on, of course. And talk to me about domain and range. Well, what I came up with was that the domain, looking horizontally on all of those graphs, it seems like the graph is covered from the left to the right, infinitely in both directions. There's no stopping point. There's no jumps, nothing like that. And so the domain is all real numbers. And kind of said this before when we looked at some graphs just making a t-chart. I can take this base and raise it to any number, positive, negative, 0, whatever at all. Doesn't matter. The exponent can be any number. But when I raise it to any number, the output values seem to fall in place only above the x-axis, only greater than 0. And we've definitely seen this before. So I'm seeing this range as greater than 0. So as I said, that's a huge thing conceptually for us in this unit, is that the exponent can be any real number, and our output, our answer after raising it, has to be positive. Can't get it to be 0 and can't get it to be negative. Which means, of course, graphically, we have this horizontal asymptote, so that boundary right there at y equals 0. And from either direction, the graph is getting closer and closer and closer to 0 without ever touching or crossing. Either exponential growth as it goes to the left, or exponential decay as it goes to the right. All right. Good question here. Is the exponential model 1-to-1? So 1-to-1, everybody, would mean it would have to pass the horizontal line test. And I guess I'll redraw. There's exponential growth. There's exponential decay. Does this one pass the horizontal line test? Absolutely. Does this one pass the horizontal line test? Certainly. And so as a result, our exponential models are definitely 1-to-1. Which means, of course, if you remember our connection, if the function is 1-to-1, then its inverse is a function independently. And as a matter of fact, kind of the second half of this unit, we'll be focusing on the inverse of this exponential model right here. And then I guess I just put this into play. The y-intercept is always the little a value. I kind of kept it at 1 there. So just put that in place, and that's good. So little a is going to be your y-intercept. Keep that in mind as we go through the next several problems here. I know that's going to come up. All right, so those are the good characteristics here. I'm going to go right into my next example. And let's see if we can start putting some things together, write an equation for each graph. You'll help me out with some of the numerical values here. A and B pretty much go hand in hand. They're basically the same problem, except for the fact that one is growth and one is decay. So everyone, if you would, give me a y equals a times b to the x, and let's write an exponential model for each graph. So let's label a couple things, and obviously we do know. At this stage, you should understand that we do need a numerical value for a, we do need a numerical value for b. X and y, of course, represent our variable quantities for the infinite number of points on this exponential curve. So, first order of business, everyone, I see that there's the y-intercept there at +4. Everyone, now let's get this moving. That's little a. So what we just determined is the y-intercept is the initial value, and the initial value is little a. Now I don't have b. I have no idea the growth factor per time period, no idea. But I do have something I can work with. And so there's the x, and there's the y. And so I can use that. We've kind of talked about this before, where if it is a point on the curve, then very simply, it makes the equation true. And so we can use it. So let's see what I have going there. And let's see, b, and looks like raised to the 4th. Okay, very nice. Well, I just want to make sure I have my numbers correct there. Looks like I do, I suppose. So let's go for it. Everybody, if you would, I think we want to divide that on over. So I'm going to go ahead and do that on the calculator as well here. Let's see what we get. So let's clear this out. And everybody, I'm going to do 41.9904. And how about we divide that by 4? Okay, and I get that piece right there. So I'm going to write that 10.4976. Okay. Now the question then becomes, how am I going to get that growth factor per time period? How am I going to get b? Well, I think in this case, in order to undo raising to the 4th power, we're going to apply the opposite operation, which would be the root. And so we're going to end up doing a 4th root on that. And let's see what it gives us. So if you forget how to type in a 4th root, let me refresh your memories. Everybody hit the number 4 on the calculator. And then you go under the math menu. And does everyone see the x root right there? So let's go ahead and highlight that. And so I'm looking for the 4th root of 4976. Wonderful. And it looks like I get 1.8. And so our b value there works out nicely. So this would be the growth factor for 4 time periods, but there's your growth factor per time period, 1.8, an 80% increase if we were to go that way. So everyone, let's go ahead and put this in. I think we're ready. I have 4 as my y-intercept times 1.8 and then raised to the x. Excellent. Exponential growth. Our b value is definitely bigger than 1, and that matches perfectly. Okay. Let's go ahead and do letter B. As I said, letter B is virtually identical here, so let's go ahead and play it the same way. Obviously, the fundamental difference is that it's exponential decay as opposed to exponential growth. But let's get this going. Let's label what we have. Everybody, there is little a. So the initial quantity, there's our y-intercept. And again, I don't have a b value here, unfortunately, but I do have an x and a y that I will hopefully be able to use. So let's start it out. Let's plug in what we know and solve for what we don't know, which is definitely b. So 24 is my a value. Trying to read the board there. It's just a touch fuzzy. I've got make sure I have that in the right spots. So I have the x value is 5, and the y value is 1.86624 from what I'm reading there. And so I think what we'll probably want to do is divide by the 24 and then undo raising to the 5th by doing a 5th root. I'm hoping everybody agrees with those 2 steps again. Divide by the 24, and then I'll get b to the 5th. And how do I undo raising to the 5th? I'll go ahead and do a 5th root. So let's see. Let's play that out completely and see if it gives us what we're looking for. So I do that. Divide by 24. Get that answer right there. Now, everybody, I'm going to do a 5th root on that number. Interesting. I have a very small number here, pretty close to 0. I'm going to do a 5th root on that. And so type that in however you want. 5th root of 0.07776. Ooh, and it works out nicely. I get a b value of 0.6. And was that what we were expecting, by the way? Well, if it is exponential decay, should we be getting a number between 0 and 1 for our b value? Of course, absolutely. So this works perfectly. And so as a result, I end up getting something along these lines right here, 24 times 0.6 raised to the x. If I asked you about the percent decrease per time period here, this looks like it would be a 40% decrease. 1 minus 0.4 would give us this value right here. All right, so growth rate here above 1, decay rate here between 0 and 1. Nice. Let's go ahead and do part C. Significantly harder, but I think we have the algebraic background to be successful with this. So notice in this case, and I'm not going to speculate as to what this is because it's not labeled, I don't have a and I don't have b. What I do have is an x and a y. So what I'm going to do, everyone, is this. I'm going to write y equals a times b to the x, and I'm going to plug in what I know. I don't know a and b, which is not good. I have that, and I have that right there. All right, 1 equation and 2 variables. Not a great position to be in. I don't have a and I don't have b, and so in this single equation, there's not much I can do. So the question, of course, becomes, what can I do with the secondary piece of information? Well, guys, this is an x and a y, and I plugged it in. This is also an x and a y. Could I plug that into another y equals a times b to the x and get something along these lines right here? So 1 equation and 1 variable, one equation and 2 variables, no good. But 2 equations and 2 variables, yeah, that looks pretty good to us. I see something good here. I'm hoping you would all agree on that. And so what we want to do now is solve for a and b either through the process of elimination or substitution. Now, you can go either way on this. If you pursue one path and I pursue another, that's fine. No worries at all. But what I'd ask us to do is to treat this as 2 equations, a couple variables, and try to solve for one, plug it in, and then solve for the other. So I'm going to go ahead and do a little substitution here, if that's all right with everyone. And what I'm going to basically do is say that a is equal to this right here. So in that equation, that's what a is equivalent to. And so what I'm going to do, I've done this certainly before, I'm going to circle that piece and draw the arrow going to the other A. So if that is what A is equivalent to, then it can replace the A in the other equation. And so now, everyone, as I said, one equation in two variables, not good. But one equation and one variable, which now I have, oh, that's a position we can manage. And so it might need to be cleaned up just a touch here, and I'll definitely go through that. But I think we can go ahead and pull this off at this stage. So what I'm seeing, everyone, is this. Let's go start to take this piece. B to the third over B to the negative first. I'm getting everybody as B to the fourth, by the way, on that. Hopefully that works for everybody. And now 2 steps. Let's make it happen. Divide, fourth root. So I'm going to bring the calculator up here, and please work with me on this piece. So I'm going to go ahead and take the 6.75 and divide by 1.33. If I remember when I created this problem, I really did want it to be 1 1/3. So this is rounded a little bit, but hopefully it'll still work out for us. And then, guys, I'm going to go ahead and fourth root this. So I have B to the fourth at this stage. I do want B. And so everybody, if you would, fourth root that answer. And I remember now, yeah, I sort of wanted it to turn out to be 1.5. So if you don't mind, I'm going to truncate this off here and just treat it as 1.5 because I know that's what I wanted essentially in the end. So I'm getting a B value, everyone, of 1.5. Excellent. So 2 things to solve for, A and B. We definitely found 1. Now I would love to go back and put that in. I'm going to do another circle here. If you don't want to, you don't have to by any means. I see this is a good place to put it. And so just whatever 1.33 divided by B to the negative first is, or in this case 1.5 to the negative first, should be able to give us our A value. So again, just putting this in for B and solving for A. So as mentioned before, this really should be 1 1/3. I'll deal with that in just a sec. We'll see what comes up here. So raised to the negative first. Use my B in order to find A. And I think I wanted it to be 2. So let's go ahead and do that piece. So A would be 2. And now we're ready, everyone. Here we go. Y equals 2 and 1.5 raised to the X. Okay, so 2 points on the exponential growth curve here. Still, I think we were able to solve nicely. This model right here would match that curve perfectly. Those points would be plugged in nicely. All right, so good. Just relating some of the graphical aspects and putting it in terms of the model. Wonderful. Last example here for this lesson, it's example 4. I have 2 sets of data, and just to throw it out there, one of these sets of data will be linear, one of these sets of data will be exponential. The first order of business is for you to tell me which is which, and then we'll go from there. So let's see what we want to do. First and foremost, everybody, if I'm going to play this out correctly, I think we want to go ahead and, well, see which one is linear. I'm just kind of looking at this. And so remember what it means to be linear. Linear means it's either going up or down by the same amount. So I'm looking at the one to the left here, and does it look like these numbers are going down by the same amount? So I'm going to do a little math. If you just can't see it, that's perfectly fine. But I'm going to see what the difference is between these two, and see what the difference is between these two, and so forth. And let's just see. Does it look like it's going down by the same amount every time? So I'm just going to see what happened there. It started at 11.65 and went down to 10.5. So it looks like it went down by 1.15 units. Let's go ahead and try it again on the next one. So that and minus the 10.5. Let's see if it was at 10.5 and it went down to this, it went down by the same number of units. And I guess I would ask you, do you start to see that in each case, and I'm going to go ahead and put this in, I'm going to minus 1.15, minus 1.15, et cetera, et cetera. If you don't mind, put that in there. I think that's, oops, let's do that correctly for you. So minus 1.15 all the way through, which means anything that increases or decreases by a constant rate is linear. Meaning, everybody, it's just y equals mx plus b. So this is our linear one, which sort of gives it away from the other one, but that's all right. M is the slope, the rate of change. B is the y-intercept, or the initial value. And I hope everyone sees the initial value, just kindly enough, was given. So it's 11.65. Slope is what we found. And guys, you're ready to write your y equals mx plus b. And that's it. There's your mathematical rule for this set of values right there. Given an x, you've got y. Given a y, you can get x. All right. Now, everyone, I look at this one. And by the way, I was just kind of staring at this one earlier and asking myself, is it linear? Well, here I'm going up by 1. Here I'm going up by 1.1. Here I'm going up by 1.21. So it doesn't really look like it's going up by the same amount. So it's definitely not linear. Well, let's see what we're going to go ahead and do here in terms of the exponential piece. This is going to be little a. I'm hoping everybody is comfortable with that piece. This is your initial value. That's going to be little a. But what's it going up by each and every time in terms of multiplication? What am I multiplying by each and every time here? Well, let's kind of work backwards, and I'm going to see. So what I would do here is just take a look, and, well, we started with 10 and got to 11. So 10 times something gives us this 11. Oh, 1.1. And then, let's see, what was that other one? 12.1, same idea. Let's see, now we're at 12.1, and we were at 11. So 11 times what would get us that 12.1? Oh, same thing. And so you can see in each and every case here, I'm going to multiply by that 1.1. So I'm just going to do times 1.1 right in there, times 1.1. And you would see, of course, that that's exactly what's going on in each case. I'm just repeatedly multiplying by 1.1, your growth factor. And so I think we are ready. The initial value is 10, starting at 10. And I would be repeatedly multiplying by 1.1, and repeated multiplication means that this is the base raised to the exponent. And there you go, exponential growth. So I like contrasting here. Linear growth, or in this case it's linear decay, but linear function versus exponential function. One going up or down by the same rate or the same value, one going up or down by the same percentage. This would be a 10% increase. All right, everyone. So kind of day 2 there, just tying some ideas that we worked on introducing exponential functions, and we'll certainly continue the discussion all the way through this unit. Thanks for listening, of course, and please let me know if you have any questions.